Today we are talking about waves and energy. Okay. All right. Anytime we experience waves, okay, in fact, light travels in a wave, and so that's why we talk about things like wavelength and frequency of light. Uh, a wave is just a means of transmitting energy from one place to another without actually moving stuff from one place to another. So waves transport energy. All right, so to begin with waves, we need to draw the anatomy of a wave. Ooh. Oh, come on now. There we go. Okay, so here we have a wave. Now we need to start talking about its parts. Okay. So the first thing we're going to define is called a wavelength, and a wavelength is the distance between two corresponding points on a wave. Two corresponding points on a wave. Okay, so you could take this wavelength and you can move it up. So it could be from the top of the wave to the top of the wave, bottom of the wave to the bottom of the wave. Okay, those points are corresponding, as opposed to two consecutive like level points, because from here to here is not a wavelength. From here to here is not a wavelength, but it has to be at the same point on the next wave. Okay. The next one we have is this top point up here, and these are called. These are crests. It is the maximum positive amplitude of a wave, which brings me to the next one, but. Okay, this is the maximum positive amplitude of a wave. Okay, and then down here, we have these are troughs, or troughs, or truths, or troughs, or troughs. It's called a trough. This is a trough. Okay, and it's the same as the crest, except it's the maximum. Okay, I'm sorry, it's the minimum. Well, It is the minimum amplitude of a wave as opposed to the maximum amplitude of a wave, but they're the same. The distance from the midline, right here, this amplitude is the distance from the midline of the wave to the crest or to the trough. That these are both okay. These are both amplitudes. Okay. All right. Okay. Then there's two more, and they are inverses of each other, and we can't really draw them on here, but they are called the period where did you go? There you go. Okay. Then we have a period, which is the time it takes for a wave to pass through a point. So if I'm looking at this point right here, and we have waves going through, it's how long does it take one full wavelength to pass this particular point? All right, so we have two waves right here, and if I'm looking at this point, I'm looking to see how long it's going to take to get back to this point on the next wave. How much time passes for it to get through there? Or it's how long it takes for one wavelength of the light to pass a particular point. Okay, so it's the time for one wave to pass through a point. And then if we take 1 over this, so 1 over, oh, and it's given by the symbol t. Okay, for time. 1 over the time is called the frequency. And we will use either F or the Greek letter nu, which looks like a V that's moving really fast. Okay, it's the Greek letter nu. And instead of being the amount of time it takes for one wave to pass through a point, frequency is how many waves pass by every second. Okay, or whatever unit of time you want to use. So for example, RPM in your car is a frequency. A revolution counts as a cycle or counts as a wave unit. Okay, so an RPM is revolutions per second. That's the frequency of your car. In fact, we talked about the Doppler effect the other day, right? And we talked about race cars that drive by and then the pitch of the sound that you are hearing is equal to the RPS of the car, the revolutions per second. So take the RPM divided by 60, and that's how many revolutions per second there are, and that's the exact pitch that you hear, as if like a music pitch. That's why it has that sound to it. Okay, so waves transport energy. Albert Einstein won his Nobel Prize, not for relativity, not for general relativity. He won it for this. He found what's called the photoelectric effect. He discovered that in certain metals, if you shine light on them, they will give off electricity. And not only will they give off electricity, they'll give off electricity to the point where, they won't give off electricity, they'll shoot out an electron. It's a little different. And that electron will have an amount of energy equal to, or proportional to, the frequency of light that hits it. Okay, so here's this piece of metal. And there's incident light, is what it's called. Okay, and if the light has, if it has enough energy, it can kick off an electron. Okay, but it has to have enough energy. And so he started shooting all kinds of light at it. And he found that for different metals, there would be a frequency, a threshold frequency of light where it would start to do it. And the energy of the electron that would shoot off would be proportional to the frequency of light. Now, that brings us to our spectrum, which we guys know is red, orange, yellow, green, blue, there is no indigo, and violet. Those of you that have learned Roy G. Biv learned it somewhat incorrectly. Isaac Newton actually discovered that white light has all of the colors of the rainbow. However, when he discovered that there were only 6 colors of light, and when you start looking at color, how many of you have taken art? You've studied a color wheel. You've done a color wheel before. How many colors are there? Well, no, right. There's only 6, right? Your 6 primary. You've got your 3 primaries and your 3 secondaries. Yeah. Okay. Where's indigo? Okay. It's not there. He's lying to you, and the reason he's lying to you is because 6 was too close to being an evil number. Like if you put 3 of them next to each other, it's the mark of the beast. Now, I apologize for those of you that take this seriously, but the science is the science. There's only 6 colors, but Sir Isaac Newton was a very devoutly religious person, and he couldn't have 6 being the number of colors for something so beautiful as light. And so he introduced and he made up the idea of indigo fitting between blue and violet, and it's really a load of hooey. That it's there. It's not. It's these 6 colors, these 6 main colors for your rainbow. Okay. It's actually all of the colors in the world, and we just have regions that we call, but that's a whole other issue. The big thing is, violet light has a very high frequency, has a large nu. Red has a low frequency. Now, we also know that it extends out here, because then we have infrared, and this way we have ultraviolet, which is your black light, which you asked about the other day, the ultraviolet. You can't see these. Although we do have some species on the planet that can see an ultrared. Okay, snakes, for example, have a special sensor that sees an ultrared. It's their pit sense. You ever see a little disc, a round thing on their snouts. That's just behind their nares, just behind their nose. It's their pit sense, and they can sense heat. Ultraviolet, bees and some other birds can see in ultraviolet. In fact, bees only see in ultraviolet. And so if they look at a flower, it looks entirely different. Okay, take some flowers under a black light sometimes and see what they look like. And it's totally different. They like totally change color. It's pretty amazing. But this right here, part of our spectrum, is here's red. Here's purple. Okay. And then we have the rest of the electromagnetic spectrum. Radio waves, cosmic rays, X-rays, microwaves, all of these different waves and different forms of radiation that you heard of are all just versions of light. And they all have an energy associated with them, and it's associated with their frequency. And so the higher the frequency, the more energy the light has, the more energy the light is carrying. Gamma rays, that we've talked about before, as part of a radiation, are way over here. Gamma rays are a form of light, or a high energy form of light. Okay. Oh, sorry. The amount of energy is determined by this equation. The energy equals H, which is called Planck's constant, and I think I'm just only referring to it because I think you're going to see it on your PDawg today. Times the frequency. Okay, this amount right here is the amount of energy from a photon of light, a single photon of light, which is a teeny tiny little packet of energy. Okay, it's like a particle of light, which is where we get kind of weird, because now we start talking about wave and particles, about light, and that's a lecture for another day. This frequency also gives us, if we multiply our frequency times our wavelength, which I didn't tell you guys, that our wavelength is given by this this lambda here, this Greek letter lambda. It's like an upside down Y. Our frequency times our wavelength equals the speed. The speed of light is given by the letter c, and it equals 3.0 times 10 to the 8th meters per second. Which is really fast. In fact, it is the cosmic speed limit. Thou shalt not go faster than the speed of light. With some caveats in there. You can't go faster than the speed of light. It's impossible to do. You reach infinite mass when that happens. So, this is our frequency times our wavelength equals our speed of light. Okay, and we can get our frequency from h nu, which is the energy of a photon of a particle of light. And we'll deal more with this with your assignment tonight. Frequency, wavelength, speed of light, 3 times 10 to the 8th meters per second.